Which one was it? 3239. All right, good morning, everybody. Hope you had a good weekend. Anyone get a chance to play in the snow? Anyone build snowmen, snow forts? This was some really good stuff for building snow forts. Goodness, great big piles of it too. No? I guess not. All right. Well, finish your homework early today and go build a snow fort, okay? Have some fun with it. Right, so we just finished chapter 1. We had our test last week, the two parts, the quest multiple choice part and the two free response problems that you turned in. I've been asked about going over answers to those. I will review answers to the two problems tomorrow. We'll go over those in class tomorrow. Grades for those should all be in. And since I was focusing on that, I didn't quite get caught up on the other schoolwork. But the test grades should be in, so you can look at that. If you have any questions, feel free to email me, ask, I know, and I can explain anything, how I got the points from where. I tried to give as much partial credit as I could. So even if you only got, say, half the problems, you actually got more than a 50% in that section if you had some work on the other one. Okay, so I was very generous with the partial credit here. That said, I think that's everything I needed to cover this morning. So let's dive into chapter 2. Okay, and chapter 2 is a big one. All right, we're going to take all that problem-solving knowledge and all of those basic skills that we started looking at semester 1 and really dive in. Section 1 of chapter 2 itself. It's fairly dense, okay? This is one of the main reasons I started doing the read-along videos. It's not really for chapter 1, but it was for like chapter 2 and on. When he's just throwing all these things at you, it's a lot of stuff to take in, which I think it's helpful that we've seen most of these once already. Okay, so we're already getting a second look at this undefined terms, definitions, postulates, right? All these new words. Well, I hope definition isn't a new word, but you know what I mean. And it all comes down to this, right? The reason geometry is structured the way it is, the axiomatic system, the reason we do the proofs, right, is this philosophical question: how do you know something is true? And you can ask that in any class, right? Right? In English class, how do you know something is true? Well, you communicate as such. Truth comes out of communication, right? If you have effectively communicated your ideas to one another, it's a true form of communication. Okay? Science class, how do you know this scientific conclusion is true and valid? Right? You have the scientific method. That's the central route towards truth there. History, how do you know something is true? Well, you have all that historical evidence and you cross-reference the documents and, well, this thing supports this thing, but this other guy wrote and said, no, it's the other way, right? And you discern that, right? The good old document-based question if you're in AP, okay? That's how you do it in history class. How do you know something is true in math class? Well, turns out there's a reason a lot of historical mathematicians were also philosophers. Because in order to know that one fact is true about math, a lot of them depend on some other fact, right? You can't know that 2 + 2 = 4 until you first know what does 2 actually represent. What does adding actually mean? Right? And for some reason or another, we've decided as an education system that we really only dive into this structure in geometry class, even though it does exist in algebra, and middle school math is a lead up to algebra as well. All of these things, these relationships, these statements about numbers, quantity, right? Most of them are theorems, okay? Most of them are theorems. And again, I kind of mentioned this in the video, theorem is not a theory. It's not something we think, maybe, okay. No. We're pretty confident. These are all statements about, I'll just say math. And by math, I mean relationships, quantity, shape, space, right? Depending on which category we're talking about. All those things that we studied what math is falls into there. So it's just a statement about something. That's a theorem, okay? About a specific relationship. And most of those theorems rely on prior facts, these postulates and axioms, okay? These are also statements. But they are the most basic statements. We cannot prove them. They are too simple or obvious. Okay? It's something you have to get by observation about. Well, it's a statement of this is how the numbers are. Okay? There's no further breakdown you can go, except, of course, to define all of the terms involved, right? Okay? Definitions, again, okay, give, they clarify the vocabulary. That is their purpose, so that we can take shortcuts and say this single word to mean all of this, right? And it has to do with communication. But even those, as the book describes, right, every definition depends on definitions of other words. You look up something in the dictionary that says, oh, the gobbledygook is of or pertaining to the act of creating a relationship with furcatar. You're like, what the heck is a furcatar? Then you got to look up furcatar, right? And you go one definition to another. And if you keep doing that back and forth, eventually you're going to get back to gobbledygook. And so mathematics, we've decided that some of these terms are undefined, okay? They are like the postulates and axioms, okay? They are vocabulary. That we accept, okay? It's too obvious to further reduce and define. It's like, well, it's this thing. Here it is. Here's its properties. I can tell you what it is, but I can't break it down into any further. This depends on that. It is the starting point. And we have to have a starting point everywhere, okay? To bring up yet another example, right, because this is a Catholic school, theologically, we have a starting point. That is God, right? Everything we believe about religion, right, stems from that worldview that you first accept that God exists. Okay? That's the basis for the rest of Christianity. You have to start there. Right? And the origin of the universe and all of having mathematics and science and English, the fact that we have all of these discussions and are able to do this and have bodies and minds that can think and communicate with each other comes from, well, God created the universe. There was a beginning. Right? Regardless of how long you think it took, we still all accept, right? God started it. Okay? So it has a starting point. It's not some infinitely, well, it just continued forever and ever. It's like, no, there was a definite begin. Okay? That is our undefined term. And from that comes everything else. All right? And so we can take that, and now the rest of that section gets into, okay, now that you've got the undefined terms, definitions, postulates, now let's start building something. And the very basic building pieces of geometry comes from, well, first, points, lines, and planes, those three undefined terms. but most of the things we're familiar with are made out of segments, okay? Not an infinite line, just a portion thereof, the segment, okay? And we're comparing that segment to other segments, okay? This is what gets us the ruler postulate, the idea that, hey, I could take this segment and I could line it up with the number line of putting numbers in order, okay, and call it a ruler, and thus I can measure things. And now I have a comparison of size and length of segments, right, depending on how many integers of the number line I can fit along that, assuming they're evenly spaced, right? And then angles come out of, I can take one segment. What if we put two segments next to each other? We connect them only on one end. If you connect them on two ends, well, then they're on top of each other. Connect them on one end. And now I created an angle. And the segments and angles form everything else in geometry. Okay? Everything we do, all of the fun, cool shapes, building stuff, architecture, all around us, right? It's all going to be segments and angles. So let's dive into a couple example problems for today and explore some features and aspects and applications of segments and angles. Here's our first one. A child leaves home and arrives at school after walking 6 blocks due south and 8 blocks due west. Find the approximate bearing of the child's home from the school. Draw a diagram and measure the angle with a protractor. Okay. Now, seeing as I don't actually have a real protractor, well, I could get one out of the cabinet, hand it, but I don't have a visual one. This is going to be a little tricky to show here, so we're going to do our best. But first we have to understand, okay, leaves home, arrives at school. Oh, they go from home to school. But it says find the bearing of the child's home from the school. See that? Home from school. So we go from, let's draw a diagram, from home to school. And by walking 6 blocks due south, okay, well, we got to understand our directions here. We've decided by convention, north, south, east, west. So from home, he's gone south. Oh, so I should put this one up here, right? He went south. How much? 6 blocks, right? And 8 blocks due west. So that would be this direction. And so school ends up right there. Okay? From home to school. So we've got to, in order for this to make sense, think about foundationally what all has to happen here. You have to understand, right, not just interpreting the written language back into the mathematics, but understand that the math concept's happening here, right? A segment of length 6. What does it mean to have a segment that has a length 6? What does that rely on? What does it mean to have another segment of length 8 in a different direction, right? West instead of south. Perpendicular directions there, okay? This is a right angle. So we're incorporating an angle. Find the approximate bearing. What is a bearing? You've got to understand that term. From home to the school. So we want to know what is the net result of going from home to the school. Let me use a different color here. Right. Let's say his pet parrot escapes home and through some innate sense knows exactly where he is and flies straight there. He doesn't have to follow the blocks. He doesn't have to walk down the streets. He can just fly right over top of all the buildings straight there, right? Which direction is the parrot going to fly? It's certainly not south. It's not west. It's something kind of between south and west. Is it exactly perfectly southwest? That's what we're trying to figure out, okay? And if we go to the text here, let me go back to where they introduce, I think they had bearings in here? Did we have bearing in here, or was it just within the problem? And I get that. And then this one, talking about the turning ship, doesn't introduce bearing. Okay. So one of your problems tonight, your homework, introduces bearing. Right? You're going to do number 29. The bearing of a line segment is the acute angle that line makes with a north-south line. A north-south line. Okay? So we've got to compare the direction we're going to the north-south line and find the acute angle there. All right? Because there's always two possibilities. Okay? So let's draw in my north-south line. Okay, here's north, here's south. And we could, right, just look at those. Okay? Notice I have two angles here. I've got this angle up here and this angle down here, only one of which is acute. We can tell from looking at it. One of them is smaller than the other. We're going with the small one. So we need to find this. And I'm going to use the Greek letter theta to represent my unknown angle. We want to know that distance there. What? Now, we could compute this. We could figure this out. Use a little bit of trigonometric mathematics here, but that's not what they asked us to do. Okay, they said, draw a diagram and measure the angle with a protractor. Well, how the heck am I going to know that my random drawn diagram is going to be any good? I need to make these measurements, the only measurements the problem gives me, to be as accurate in my diagram as possible. So I go from given measures to an accurate diagram, and then I can measure from the diagram and trust that that measurement is reasonably accurate. Does that make sense? So we've got to find a way to create a better diagram here. So here is what I'm going to do. I'm going to use, let's say, not the lime green, just the light green. I'm going to make a square. And I'm going to duplicate that square just using the technology here. Oops. Just move it. And I'm going to create a grid here. Okay? That way I know every direction is the same size. And I need 8 squares. 1, 2, 3, 4, 5, 6, 7. One more. 8. And now let's move all those down here. Pick that square and duplicate it. And we'll have 6 going up. 3, 4, 5, 6. Okay, so I've made use of the ruler postulate, okay, to say I'm going to create a line segment here, right, this line segment right down here, and I'm going to decide that that is 8 units long. And I'm going to match that same width, okay, and I'm going to turn it vertically and say this is 6 units tall. And now when I draw in, we got to match a corner to a corner. So as long as I take the top left corner to the top left corner, that will be accurate. So I want to compare that to, right, this vertical line, so I need to find that angle. So I'm going to need some kind of protractor. Let me whip one up right here. It's going to have to be somewhat vertical, and because it's always going to try to draw some kind of parabola. It doesn't do half circles very well. But I can get a perfect full circle. There we go. We'll just draw down through the middle. We go. And I know that much is 90, right? And here is my center point. This would be 0, halfway would be 45. And we can do halves. The human brain is pretty good at approximating halfway. No, I want to draw on it. Thank you. Right? And so I can just keep dividing this in half each time, and we'll work out what that actual number is. Right? I don't need to do more work than necessary. Let's make this a different color so we can see it. I'm going to pick this up and put my center point right on there. Line it right up, and oh, look at that. That's looking pretty close to my point right there. So it is one increment more than 45. So halfway between 45 and 90. Half of 45, half of 40 is 20, half of 5 is 2.5, so 22.5. Okay, so 22.5, that would have been right here. So this guy is 45 plus 22.5. Well, I'm not there. I need to take half of that again. So half of 22 is 11, half of 0.5 is 0.25. So we take that much more than 45. So 45 plus 11.25. And now I'm going to get 56.25 degrees. That is my guess there. Okay? That's my measurement. And I'm pretty confident in it. I think that's going to be pretty close. Within, a few degrees, right? It's a sketch, it's a drawing, so I would not trust it to that quarter of a degree. That's add between 54 and 58, I'd say is reasonable, right? Somewhere between, how about this? Theta is between 54 and 58, give or take 2 degrees. I'm pretty confident there. I think that worked out well, right? Use an actual protractor. Yours will be a little bit more accurate because you don't have to use the sketched up protractor. That's losing me some accuracy there. But this part is still pretty strongly accurate, okay? There is no good reason you can't create an even 6 versus 8 ratio. All right. Any questions on that problem? No, let's take a look at another one then. This is a classic math problem scenario dealing with the hands of an analog clock. I know a lot of you are probably used to digital clocks now, but it helps to still be able to read an analog clock. And there's a lot of interesting mathematics going on with the angles between the hands. So, of course, it's full circle, divided into 12 hours, and then further divided into 60 minutes. So the first question, after 1 hour, through what angle has the hour hand rotated versus the minute hand? Okay, 1 hour. So the hour hand goes from 2 to point at 3. So it's gone through, well, each hour is 1/12, right? So it's gone through, let's go back to blue. 1/12 of full circle is 360 degrees. So that would be 30 degrees, okay? How about the minute hand? For 1 hour to pass, how far around does the minute hand go? Well, the minute hand goes all the way around, so the minute hand is going to be the full 360 degrees. So there's my 2 answers there. Ooh, after 1 minute, through what angle has the minute hand rotated versus the hour hand? Ooh. Okay, 1 minute is 1/60th of the clock face, right? So 1/60th times 360. So that's going to be 36 divided by 6 is just 6 degrees. How about the hour hand, though? The hour hand In the full hour, it's gone that 30 degrees, but now it has to go only 1 minute. So 1/60th of the hour. So the hour hand has gone 1/60th of that original 30 degrees of the hour that it would have moved. So now we're down to, reduce the zeros, 3/6, we're down to half a degree. Half a degree for the hour hand there, right? Teeny tiny little bit. Okay, so that's going to give us a baseline here, because now we want to determine the measure of the obtuse angle formed by the hour and minute hands at 9:10 and 5:56. Okay, hour and minute hand at 9:10. Well, let's make a quick sketch, right? If we don't understand it immediately, when in doubt, draw. And so 12, 6, 3, 9. Our hour hand would be pointing mostly at 9, and the minute hand would be pointing at 1, 2, at 2 there. So that's what we're looking for. We want the obtuse angle, not the reflex angle. So this angle in here. Okay, I know the minute hand is the easy part. It's the hour hand that's tricky, because the hour hand is not actually pointing at 9. As we determined, each minute that passes, the hour hand has moved from 9 half a degree further along. Okay? So if you just think, well, every hour is 30 degrees, right? So 1, 2, 3, 4, 5 times 30. Is it 150 degrees? No, 150 is too much. But that's a good guess and test method, right? Okay, what would be the simple case? Here we're solving a simpler problem. What if the hour hand didn't move until the full hour completed, then it just jumps to 10, okay? What if it didn't move in increments? It would be 30 degrees for each hour number between them. It'd be 150. So we know it's got to be less than that, because the hour hand has moved. We agree? And we can write that down. Our angle must be less than 150 degrees. How much did the hour hand move by? Well, we have 10 minutes past the hour, so 10 minutes go from when it pointed directly at 9, times it moves at 0.5 degrees per minute, right? We just figured that out earlier. So 10 times a half is 5 degrees. So the hour hand has moved up 5 degrees, so it's 5 degrees less. That would make 150 minus 5, 145 degrees. Final answer there. How about, what's the other time? 5:56. Ooh, 5:56. Okay, what does that look like? Okay, on the clock. 12, 3, 6, 9. Here's 4, here's 5. Hour hand pointing down at 5. 56, 55 would be at the 11, so we're just a little past the 11. In fact, the hour hand is mostly past the 5. It's almost 6 o'clock. It's 4 minutes until 6 o'clock. I would almost say it's easier to start with 6 o'clock and work backwards. That almost seems easier to me. Think about, right, from the perfect 6 o'clock, at 5:56, how far over is the minute hand and how much further to go is the hour hand? And then I need to find this angle in here. If it was perfectly 6 o'clock, it would be 180, but I've got two angles. Let's call them angle A and angle B. One for the minute hand, one for the hour hand. Take a looking at that. From the 180, the minute hand is farther out, right? It's farther over this way, so I would have to add this. So we're going to add whatever A we find. But the hour hand is moved in that, so we have to subtract the hour hand's movement from 6. Is this the easiest way? I don't know. That's the first thing that came to my mind, and I still think it's going to work, so we'll try it. Okay? No point changing direction until you come to a real stumbling block. All right? So let's do minute hand first, because the minute hand is usually easiest. At 5:56, okay, we are 4 minutes short of 6 o'clock. So the minute hand has 4 minutes to go. How many degrees does the minute hand move per minute, right? That's 6 degrees per minute. Okay, so our little angle A is going to be 6 degrees per minute times 4 minutes. So we're going to get 24 degrees. How about B? B is still 4 minutes short of matching that 6. It's still 4 minutes, except the hour hand only moves, right, half a degree per minute. So 4 times a half is 2 degrees. So B is 2 degrees. All right, so 180 plus 24 minus 2. 180 plus 24 is 204 minus 2 is 202. Wait a minute. Oh, that's not our final answer. That's not an obtuse angle. At 5:56, the minute hand looks like that. The hour hand looks like this. Not even. It won't let me draw because it's trying to snap to be perfect there, but it's almost vertical. The smaller angle is on this side. Ah, shoot. Does that mean I got to start over? No. What I have found is the angle on this side, the reflex angle. I can simply take 360 minus 202 to get my real answer that I'm actually looking for. Okay, whew, saved it there. All right, 360 minus 202. 300 minus 200 leaves me with 160 minus 2 leaves me with 58. 158. I'm going to check. Yes, that is the official correct answer. 158 degrees. We've done it. Whew. Any questions there? For the sake of time, I think I'm going to leave out or part D. You can have at that one if you would like. During what hour and minute after midnight will the hour and minute hands first form a right angle? Okay, so think like 3 o'clock would definitely work, but there's going to be one before that. There's going to be a couple of them before that, actually. So what's the first one after midnight? Just ticking around. Where does it form that 90 degree? Okay. I'll let you figure that one out. You have everything necessary. Thank goodness we're not dealing with the second hand here. Oh, right. Part 4, problem-solving process. How could this get worse? The second hand. Right. The fractions get even smaller. We have to deal with that. All right. But clock math, good fun. Okay. We still have About 10 more minutes. I will leave you to get started on your problem set. We will continue to work on this problem set tomorrow. So don't feel like you have to rush it, but do go over, look through each problem today or tonight so you can come in tomorrow with questions about them and get those worked out so you will be able to confidently find the answer tomorrow. Okay? And they're not all truly problems. Some of them are more like exercises because they're basic angle stuff, all right? But that's enough for me for today. I'm going to end the stream.